So I would like to talk about polarity. So, which means that negative and positive. So in the very beginning of the class, so Bob just mentioned that, okay, let's look at the intuitionist propositional logic, and let's look at the negative fragment and positive fragment without really explaining what's going on. So let me see if I have enough time to give you a rough idea why something is called negative fragment and something else is deemed positive. And so the idea is a polarity, which means that the negatives and positives. And this idea has appears in various contexts, including type theory, category theory, and what's the other? Okay, I forgot. Anyway, and I'll give you the correspondence. The appearance of this idea in different forms in different theory. So let's look at the type theory first, because this is the type theory class. So let me try to draw a large table. So TT for type theory. No. Type theory. So what is? It's a little bit weird to start with negative instead of positive, but I'll follow Bob's order. Okay. So what is negative? It means that the definition of a particular type is based on the usage of that type, which means that it's focused on the elimination rule. And then after that, you're kind of forced. You're forced to come up with another set of introduction rules so that they are in harmony. So the idea is that the essential part of if an essential part of a particular type is kind of based on the elimination rule or the usage of that type, then usually we feel that it's negative. Is that clear? I'll give you an example, and to see why those constructs in the negative fragment are really negative. And so the counterpart of the negative types are positive, which means that it's focused on the construction of that type. So, which means you start with the introduction rule, and you derive the corresponding elimination rule so that they are in harmony. So let me give you some example. Actually, we just reviewed the construct we have in the intuitionist propositional logic. So let me give products. A times B is negative in our presentation. So why is that true? So it means that we have to think about elimination rule first. So what are the elimination rule? It means that if you have M, which is a product, then I can use it in two different ways, which is first and second. So I will claim that if you think of a product type in terms of the usage of that type, then by harmony, you are forced to have an introduction rule like this. It must be a so let me think about it. Okay, this is the better way to say it. Because there are only two ways to do this. So in order to specify a term in a product, it's sufficient to specify all the results of the usage. right? The essential part is the usage of that term in a particular type. So if I specify all the outcomes of any usage, then I specify a unique term in some sense. So what's that term? So in this case, let me give you a name to that. So n to this, well, n1 to this, and n to this. So it means that if I read it out like this, where this means the result of the first projection, and this means the result of the second projection, and I can that by writing down the two terms in tuple, I already specify all the outcomes of the usage. So this is kind of forced. If you feel that I have to give two projections, then by harmony I need to give this form. And it will be in type A times B. I hope that this gives you a kind of feeling that we start with projections, then we come up with tuples. Is that clear?
What if we decided the elim for cross should be split? Would that make any difference?
That will, the products can be presented in two ways. So in the other way, it will be positive because you are beginning with the introduction rule. Then you derive the corresponding elimination rule. Is that clear? But in the presentation of this class, Bob decided to present prototypes as a negative type. So let me just give you one more example about negative type. Oh, by the way, the top is just a special, if you have n-ary products, the top is just a special case of this, where you don't have elimination rule. So if this is, wait, what's the notation? T or 1? T? That's the.
Type is usually 1.
Okay, I'm not sure. It's either T or this or star or whatever. Then there's no elimination rule at all. There's no elimination rule. So you don't have to specify anything. And if you have n-ary products, it means that you have n way to project things down. So you have to specify n terms here. Okay, so let me erase this part because this is kind of boring. Another one is A to B, and usual formulation is always negative. You can also make it positive, but I don't think we are able to cover that in class. So what does it mean that you have a function? Again, you start with the usage of m. So how do I use that? It means that if I have term of type A, which is the type of the argument, then I have a way to use it by applying it to an argument. So I start with the usage of this term. Then I said that, okay, to specify the did I make a mistake? Oh, sorry. So the lambda symbol, and I'm using out all the available p. So this one is a valid construction of the function types because this part specifies the outcome of the usage of application. So actually you start with application, then you kind of reverse engineering the proper introduction rule to make it happen. I don't know how to give you a better intuition, but that's basically how it goes.
You also look at this in terms of like whether the intro or elim rules are invertible?
Yes, so that will be another rule of that. Oh, I see Bob is coming. Wow. Let me wrap up this quickly. So, in category theory, so we already gave you some diagrams about this elimination and introduction. Then the negative types, it means that the universal property is basically mapping in. Let me just give you an example. So if you have C times A to B, it's F, and so this is a universal property with A times A, and that's F, and 1, oh sorry. Okay, I think I will make mistake somewhere. So you can see that this is the thing we are interested in, and the map is mapping in. If you look at other diagrams, the positive part will have something mapping out from the type we are interested in. And there are also other rules here, and one of them is the thing Alba mentioned, that it also has something to do with invertibility of the rules in sequence calculus. If the left rule is invertible, then it's positive. If the right rule is invertible, then it's negative. But I don't have time to cover this. Okay, that's it.
Okay, thanks. Sorry, I'm a little bit late. Okay, so what Favonia said, those are all good things, good remarks. The business about the left asynchronous and right asynchronous connectives in logic, maybe some other occasion we'll find to talk about that. So, but that's a good remark to keep in mind for those of you who know about it. So let me erase. I guess the moral here is supposed to be that, again, we find that certain kinds of structure emerges in slightly different forms and different disguises in the same setting, and the same structure in 3 different settings, and so we sort of find that grounds for feeling that there's something fundamental going on. Okay, so where we got to last time, I'll just remind us a little bit. So the recap from where we got last time is we were looking at the dependent, and this is probably what prompted some of those questions, dependent formulations of, so the one case we did the negatives. So we had pi, principally pi and sigma, generalizing the function and product, you could say. And then we looked at the formulation of the positives, where the type itself doesn't change, like plus doesn't change, or nat doesn't change in terms of its introductory forms, but the elimination forms have to be generalized to induction principles. So the idea is that elims become induction principles. And we spent a fair bit of time of talking about that. So just to remind you, we gave an example, and the example was if we look at the elim for the Booleans, let me write it as bool, and we can cover, we have a dependent on bool, we have a family of types, let's call it C, and if we happen to have a case that holds for true, this is just by way of reminder, and a case that holds for false, where we propagate the knowledge of which branch we're in, then, and I'm not writing all my gammas and stuff down, I'm just sketching briefly, if M and P would then have type M, whatever M is, M for ZC. So that's important. So what we see over here is the idea is that the information about the branch flows into each branch. All right, which branch, I could say, which branch flows into each branch. So maybe that's a nice sounding way of saying it. Okay, is that you know when you're type checking each branch, you know which branch you're in, so to speak, because the flow information that you've gained from doing the case analysis is propagated into the type. Okay, so that's unusual from the point of view of very ordinary programming languages, but it's of the essence in dependent type theory. This is what we've done. And then, as I mentioned, viewed logically, what this is saying, so from the point of view of logic, logically, what it says is, if you want to show M for ZC, given that M is a Boolean, this is the most general of cases, then it suffices to show, meaning show that this is inhabited, so I'll just like write it like that, or I could write that as true if you want to say it. It suffices to show that true for ZC is true, and that false for ZC is true. And then in that case, it's true in general, so it's true for whatever your M is, and who knows which one it is. So then it's very clear that that's an induction principle, right? Because that's the kind of, that's what it's expressing. Of course, the induction for Booleans is kind of degenerate in a way because it's strictly a case analysis, but it's nevertheless an induction principle. Okay, so that's where we were last time, as we built up that apparatus. And then the thing I want to talk about today is I want to begin to broach, again, the subject of what are called the identity types, which you can think of as the base case for all of this stuff, because where did I ever get any notion of dependency even to exploit at all? How do I get off the ground? And I also want to talk about the concept of universes. Okay, and that'll probably take up our time. So these are the two things. And when I have this, I will at this point, when these two things are in place, I will at this point have what is called ITT, intuitionistic or intentional type theory, I then will have developed what is called intentional type theory. And I will then speak a little bit about its limitations, maybe, and its peculiarities, because that's going to motivate a bunch of other ideas from there. So that's my plan. That's what I'm going to talk about for today. So let's go back to the identity type. So now, the way I've set things up is I've talked about generalizing to the dependent function, dependent product, or dependent product type, or which generalize these things. And we spoke about the elims. We spoke about families of types like this. And the question is, where do these families of types come from? So what I did in order to just put in a strut in the lecture to get us going, I mentioned examples like the family of types of sequences of numbers of length n. I kind of jammed that in there just as a special case to motivate your thinking. And I also talked briefly about the identity types, which is the central thing for homotopy type theory. So I want to talk about that now. Okay. And the reason to do it, so to speak, backward like this, you might think in some ways kind of backward, is because it will have helped to have broached all of the previous subjects before I get to this, because it's a little bit of a mind bender sometimes to think about what's going on here. Alrighty. So now, what were the identity types? So the idea was we have a formation rule that looks like this. We have the type, we'll call it id AMN, which is going to be a type. Okay, provided that, well, I'll write it fully. A is a type, and M is in A, and N is in A. And I have previously mentioned to you that this should be thought of as the type of identifications of M and N, or the type of proofs. So this is the premier type that one tends to read propositionally, but I'm going to be arguing basically for quite a while, and you could even say for the rest of the semester, that one should also read this as a data type. And maybe the whole idea of HOT is to say, don't just read this propositionally, but also read it as a data type, and it's an interesting data type. Maybe that's it. That's the one-line summary of the whole course, actually. And so I do want to mention that. But one tends to read it propositionally as expressing, so this is called the identity type, or the equality type, or words like that. And I'm going to suggest some other readings, okay? So let's read it propositionally. So if we read it for a second. So if we read it propositionally, what we'll be saying is that this is the type of proofs that M and N are equal as elements of type A. So that's going to be the idea. And so this is the identity type, oh yes. And it's also called, I complain that unfortunately terminological traditions are beginning to collide now at this point in the development of the subject. So this is called propositional identity. A little bit later, like in a couple more lectures, I'll be propositional equality this is called. A little bit later I'll be able to explain to you why I'm complaining about that word, but anyway, because there's unfortunate collision, that's all. But it's also often called propositional equality. In other words, there are occasions in which we want to distinguish it from definitional equality. And in fact, as a matter of notation, just if you like, I'll sometimes write this as M equals A N because it looks a little nicer, okay? But don't lose track of the fact that it's a type, all right? It's not a judgment, okay, of equality, it's a type, okay? So somehow, at least at the beginning, it feels a little better to use this sort of more standardized notation and write it like that. But a lot of times I'll write this, but do remember it's a type. So this is just a notation for that. Okay, so if it's meant to be the type of equations of things representing evidence that M and N are equal, then the premier form of evidence for that fact is the axiom of reflexivity of equality. So it'll be written like this. So it says, if I have any M in A, then REFL of A of M, and I've certainly put this one up before. What I didn't put up before was the elim, which I'm going to do now. So this would be the id elim, intro. Okay, and this would be the id formation. Okay, which is the principle of reflexivity. Read propositionally, it just says M is equal to M, of course. And that's the only intro rule, at the moment anyway. That's the only intro rule. And I'm ending up today with ITT. So in ITT, this will be the only intro rule. And now I'll write over here the elim rule so I don't write too low. So the question is, what is the elimination rule? Okay, so how should the elimination rule work? Well, the elimination rule says, suppose I know that M is equal to N. For some reason, let's call it P. Okay? What I want to do is I want to have a mapping out property, because this is going to be a sort of propositional thing. So I want a mapping out property, which I erased that Favonia had put up earlier. I want a mapping out property for this guy, okay? Because what I'm going to do, and this is a little tricky, but in a certain way I'm going to think of the family of types. So let's write it like this. We'll think of the family of types. I'll write id blank blank, that entire family, or if you like to do it blank and double blank so that they're not necessarily correlated. So I want this two-place family of types to be inductively generated. So I want to think of this as an inductively generated family. Now, it is true indexed by two elements of A, which I won't write on the board. Okay, so I want to think of that as an inductively generated family. And in fact, I'm going to maintain that idea all the way through, even though I'm going to do things that look incompatible with that. So this is where the tricky things are coming up. Okay, so let's do this. So we're going to think of it as being inductively generated. So the idea is that this is an instance of this family, M and N. There's a particular instance of that family. So there's all possible M's and N's can go in here of type A. Here's a particular choice of them. And I have a proof that they're equal. Okay, so I want to now reason from that fact. So if I'm doing a mapping out property, what it means is I have a family of types. So now you'll see the discussion about positives and stuff will help us a lot here. So I want to map out of this identity type. So I need a family of types, okay? This is, yes, that's what I want to say. C, which is written like that, which is indexed by Z ranging over the identity type. So one can think of this as, if you think of this as data, then what I'm doing is I'm going to phrase an induction principle. I'm going to prove by induction that C holds for anything in that type. Okay, that's the idea. So in other words, I'm going to wind up with something or other is a proof of the fact that P for Z, C holds. Okay, just like I did with the conditional over there, except it's the same, only different. Okay, so what I'm going to do is I'm going to prove C of P, okay, based on an induction hypothesis, which is what goes right here. Oh yeah, sorry, yeah, did I screw up already or what?
In the usual formulation, C is also indexed by the N and N.
Yes, let me check my notes, but I don't think I wrote it out that way. Oh yes, I did. Excuse me. Yes, you're right. You're right. I hesitated there for a minute, and I knew there was a reason. I woke up late today, so I'm a little... Right, exactly. I have to have it more general than that. So let me write this in here. There's going to be P for Z. What's going to happen is, let me write it out. You're correct. Z is in the identity A, X, Y. And then I show C as a type. Right. This is the correct thing. And then what I'm going to get is, I'm going to give to C, let's plug them in. Okay, I'm going to give to C the endpoint, so to say, and P for X, Y, and Z in C. Yep. That's what I'm going. Oh, was that a? Yeah, okay, that's good. Yes, you're correct. Okay, sorry. So that's the idea. So thinking, if you just suppress this for a minute, I'm still making the same point, which is that I want the property to hold for the particular scenario I'm in. I forgot to plug in all the data. So M, N, and P are the data. So the data I have, because this is an inductively defined family, it's not inductively defined with M and N fixed. It's simultaneously inductively defining the whole thing. So if I want to emphasize the word, I'll say it's simultaneously inductively defined. We could say that because all of the instances of the family are defined simultaneously. So the data for a particular instance consists of M, N, and P itself, rather than fixing M and N, which is what I did for a moment there in a mistaken moment, fixing M and N and looking at P. Okay, so that's how we got there. So excuse my mistake there. What I was kind of thinking of was the next line. So the question is, what should be the induction hypothesis? That is, what do I need to show about C that is sufficient for this to hold in general? And at this stage, I can explain it to you in a pretty natural and simple way, which is the only intro form, if this type is inductively generated the way I'm explaining, then the only possible intro form is that you're ever going to encounter is REFL, because that's all there is. Okay, that's the definition of the type. So what you do is you say, well, it's enough to show that regardless of which element of A I'm talking about, that I have a proof, let me call it Q, how about, okay, that C holds for X, X, and REFL A of X. For XYZ, I called it C, and this is the id-elim rule. And I'm going to work with this for a minute. Okay, so this is the sufficient data, and then I'm going to plug in what this thing is. Okay, so the idea is that, and this is for reasons that will become more apparent later, this principle is called path induction, where we're using the term path right now to mean element of identity type of an id type. We'll call that a path. Those will also be called identifications or proofs or evidence of equality or words like that. But we'll call it a path right now. So reflexivity is the path that's a little difficult to draw. It's a path that goes from M back to M without going anywhere. Well, I can't really draw that. So the convention is you draw a small one and you mark it reflexivity, okay, because you're basically screwed. You can't draw it. But that's what I would draw. So that's the kind of picture. So we think of that as a path. It's telling us we can go from M to M by going nowhere at all, and that's where the awkwardness of drawing it at the board comes in. Okay, so this thing, but this kind of thing. So now I have to fill in what the proof term is. This is the elim form, and it's always by long tradition called J. It's parameterized by the motive, which is XYZC. It acts on P, and it acts by X dot Q. And we have the following definitional equivalence, which says if we take XYZC, I'll just do the beta rule, REFL A of, let's pick something M, okay, and X dot Q. So if the path really is reflexivity, then what you do is you take the point that it's talking about and you instantiate Q at that point. And if you check everything, you will see that this has type, by reading it off here, the right-hand side and therefore the left-hand side will have this type. It'll be, I'm writing like this, M REFL of M for XYZ in C. So that's the beta-like principle for this thing. And this thing is called path induction. Why is it called path induction? Because it's saying to show, so if we're given that P, you have an identification of M and N, and we want to show that, let's just write it like this, C, M, and P is true, if you read it as a logical thing, then what the rule is saying is it suffices to show generically in X that C, X, X REFL is true. Yeah, is true. Generically in X. So there's an easy mistake to make here, which will definitely confuse you, is don't think of each individual, I said this already, but I'll say it again. Don't think of each individual instance of it as being inductively generated. Think of the whole family as being inductively generated. So that's why we sort of back out to consider a generic element here, X is in A. So the idea is that you sort of reduce the particular unknown general case of a path from M to N that we don't know anything about. Reasoning about that, it's enough to reason about reflexivity. All I have to do is worry about the self loop. Now, given what I've developed so far of ITT so far, it's a little technically complicated, the rule, it's like maybe the most technically involved rule I've given so far. But conceptually, at the ITT level, it's probably not that objectionable because I'm taking this idea that there's only one intro rule. Okay? And the only intro rule is reflexivity, and you can kind of feel that what I'm doing here is inverting the introduction rule to say something in general about any path by reasoning about reflexivities. And that probably feels good. at a high level, that should feel like natural given everything we've said so far. What is going to come, however, and that's the remarkable thing, is we're going to later, not now, we're going to later introduce new forms of paths that aren't reflexivities. And yet, this rule will continue to remain valid. And that should create some cognitive dissonance, okay? Because if it doesn't, probably you're either a lot more clever than me, or, could very well be, or you actually haven't been paying attention. So one or the other, because it should make you a little nervous to do that, right? Because suppose I just added, just temporarily, just for a moment, I kind of chucked in another path somewhere, just wrote some additional rule. You would feel it's like saying that green is a natural number, and I just throw that in there and then expect induction to still work, and of course it won't. Okay, so you could say, how could it possibly be that you could throw in another intro rule and yet the elim rule remains the same? Well, we'll leave that in abeyance. I'll come back to that in a minute. Okay. First, I want to get used to. I haven't done that step yet. So right now, everything is like hangs together in a way that I feel I hope is fairly intuitive. Okay, so this is the computational content, this J thing, it's always called J. This J thing is the computational content of the principle of path induction. Just as we talked about the recursor that I mentioned last time as being the computational content of the principle of mathematical induction. So what I can do now is if I want to say something about the identity type, then the sort of go-to method is to apply path induction, or the identity elimination, to reason about it. And I'm going to show examples of this now, right now, which will come up next. But all of those could be approached as, I can think of them as logical problems, but I will also approach them as programming problems, because they can also be approached as write a piece of code that is going to look like this, some composition of J with a bunch of other things, in order to achieve a certain end. So let's stop being vague and let me show you what I mean. Okay, so that's the definition of the identity type, what we have there. Okay, so all right, so I'll leave that up here. So now the first thing I would like to do is to say that if we read this thing logically, it should be the case that the identity type presents an equivalence relation. Okay, so that's the first thing that I would like to do. So first of all, it's reflexive. That's by definition. It's reflexive by definition. In other words, I have the introduction rule. We say that if I read it logically, if you pick any m and a, id a m m is true, meaning that type is inhabited. That's the intro rule, says exactly that. So that's true by definition. So the next thing is it symmetric? And how do we prove this? So how do we do symmetry? Well, to prove symmetry is what I want to do is I want to find a function. I can write it like this. I'll write it sim a, which is a mapping. Well, I can do this generically in x and y in a. I want to say if you have an element of id x y, then you're going to give me back an element of id y x. Okay, so that's an arrow there, okay, that I'm writing. So it says, so the idea is that you can reverse, if you take an identification or a path or whatever word you use here, a proof here, it has some correlated proof that reverses the arrow, okay? So we can expect symmetry, we can expect this. So we want to figure out how to write that. And we should expect to be able to write this, which is transitivity. Okay, so I want trans, and you could guess what the type of that will be. So I will have x, y, z in A, and then I will write it in the sort of diagrammatic order, if you don't mind. Y, z, arrow, id, A, x, z. Written like that. So Our problem is to find such functions, okay? Because if I can find such functions, then it will be the case that if id xy is true, then id yx is true, and if id xy is true and id yz is true, then id xz is true. But I'm actually going to approach them as functional programming problems and tell you what the proof is by giving you a program, okay, that transforms this proof into that proof and transforms these two proofs into that proof. Okay, so that's the idea. Okay, so that's what I'm going to do. And at that point, then I would be able to say the identity type is really presenting at least an equivalence relation. It sure ought to. Okay, so that's what we're going to do. Okay, so good. All right, so good. So here's what I'm going to do here. So the easy one is symmetry, and the transitivity, I always get confused, so probably I'll screw it up. Okay, so let's do the symmetry. Okay, so we'll define symmetry. So the idea is that for symmetry, I take sim A to be sort of lambda xy. I'll just write them down just to remind you. Lambda xy in A, lambda z in the identity type of xy. And now I want to write a piece of code that shows up in the identity type for yx. So what do I do? Well, the only thing I've got to work on is z, and z is an element of the identity type. So if I want to work on that, I'm going to do a j. So I'm going to do a path induction with some motive, which I will write down, on z. And the idea should be that this thing, what should its type be? Its type should be that generically for x in A, we should have something whose type is, in this case, I did the path induction at the wrong spot, did I not? Let me think about this for a minute. I told you I would screw this up. No, I told you I would screw up transitivity. I didn't think I'd screw this up. No, this looks good. XX and REFL of x, which we don't need, which is id xx, right? Okay, yes, right. So this is going to be something whose type is id a xx. That's what I need here, because if I fill that in, then by the elimination rule, the body will have type plug in, we'll get id a, I want this to have id a yx. This is what I want. This is what I want to have happen. I've got to fill this out. And I've got something, I need to provide here something id a xx. This is what I'm going to do. So the motive is going to be xy underscore id a yx, if I'm not mistaken. That should do the job. Okay? Because the idea will be now, you're given x and y and a, and you're given z, but the z, the motive doesn't depend on z, so I wrote an underscore there. So if I successfully apply path induction, I will get something whose type is this guy with x and y plugged in, which will give me y and x, which is what I need. Okay? Now, what is the sufficiency for that? The sufficiency is that I have something which is of type id xx, and of course, that will just be reflexivity. And if I didn't make a mistake, no promises, but if I didn't make a mistake, I think that's correct. Okay, so that's a simple one. The transitivity requires a little thought, and actually, there's probably, I don't know, I didn't count them, but there are certainly several definitionally distinct ways to prove the theorem. Okay, so I will, oh yes, and let me point out one other thing. Okay, the other thing I want to note, and I can really put this in, but we'll need this remark later, is that if you look at what symmetry does to M, and reflexivity, that's definitionally equal to reflexivity. Why is that the case? Because this symmetry this application of symmetry is defined to be a J, and J has a computation rule right there, the beta rule for J. When you plug in reflexivity, will compute and spit out, well, reflexivity. So it works. Okay, so this is what's happening here for REFL A here, and we try to be careful about all of that. So we'll need that. So that's the simplest possible case. Now the thing you're no doubt asking yourself, and it's perfectly reasonable, is in some sense, There's some inevitability to this because ultimately the only paths I have my hands on are reflexivity, so everything must boil down to reflexivity in some way. And that is what's going on, because what I'm really saying here when I say the identity presents the equivalence relation, what I'm saying is the diagonal relation is symmetric and transitive. Okay? The relation that just relates things only to itself is symmetric and transitive. But in fact, the proof is more robust than that. Okay? Well, it is the same. This is a little difficult explanatory issue. Let's hold that in abeyance for now. When we add new forms of path, we'll have to reconsider what is being said here. That's what I would like to say. Okay, so now let's do transitivity. Okay, I'm afraid of transitivity because I know I'm going to screw this up, but I took a lot of trouble to write it out carefully, so let's see if I can do this right. Okay, so I called it, so I have, let's see, MNP, so let's call them, all right, let me write them like this, lambda m, lambda n, lambda p, to match up with my notes, okay? And so I have that, those are the 3 points. I have u, let's just write it down so that we record the types, u, mn, and v, which is id a and p. Okay, that's our input, and we're going to write down something here, and that something had better turn out to have type id a mp. Okay, that's what needs to go in there. Okay, so that's the idea. So this will be my trans mnuv. Okay, that I've written over here. This is what I need to write down. Okay, so the question is now, how do we do this? So we've got two different, the things we can work with. Since A is completely generic, there's nothing I can really do with M and N and P by themselves because I don't even know what A is. A is totally generic in this argument. So obviously the only thing I can possibly do is examine U and V. Okay, that's what I'm going to do. So what I'm going to do is I'm going to do that, okay, and I'm going to do it by a J. Okay, well, it's actually going to, well, there's going to be a J involved, so let me put a paren around. So there's going to be a J involved, and I have to leave a little room for this. And I'm going to do it by induction on U, and I'm going to put something in here. And then I'm going to do something with that. Okay? All right, that's what's going to happen. So just the outline of what we're doing here. So think of this as like a structure editor at the board here. So okay, so put down a template. So this is what I'm going to do. I looked up in the type theoretic design patterns, and I am instantiating the transitivity pattern here. So okay, so here's what I do. I want to write down. So here's my template. Okay, and I'm going to fill in those pieces of code. So this is my type theoretic framework. Okay, so here's what I'm going to do. So the problem is it's helpful if you play around with this, because once I tell you the answer, you'll be able to like say, oh yeah, it works, but the question is to invent it. So the trick is to come up with the motive. The whole hard part is coming up with the motive. Okay, so my structure editor will only take me so far. It will tell me there, but now I have to do the creative part. Okay, so the creative part is to have to figure out what is the motive for the induction. So the pattern that I'm working out here is I need to end up with MP, and I've got an MN and NP. And if you mess around with this for a while and do an induction on N, so you see what's going to happen is that I'm going to do an induction on this path between M and N, okay? So it's going to reduce to a reflexivity for that particular case. But when I get out of it, what I'm going to do is I'm going to plug in M, N, and U into the motive, all right? That's what's going to happen. I'm going to end up making a statement about M, N, and U. But you see, the problem is the statement I want is about M and P. It's not about M, N, and U. In other words, think of whatever I would plug in for the motive here. For this J, let's just look at the J in isolation. If I didn't give away a hint and put some other stuff here, just let's look at the J in isolation. I'm trying to build an id A MP out of this guy, this U. But whatever I do for the motive, all I'm going to get out of it is M, N, and U. And where's the P supposed to come from? Okay, there's no This is the best way I can tell that I know to motivate how to come up with this. So you come down and you say, well, I have an mn and an m and an n and a u, and I'm supposed to get an m and a p. So something is wrong because, or something is weird because, of course, the v has to be involved, and it's the v that provides the p in somewhere. So what you want to do is, let me erase to make room for a little further ascription here. What did I do with my eraser? There it is. Okay, let's focus in on the inner part here, the type of the j, and then this will, in the end, is going to have id a, m and p. Okay, m and p, right, is what I need at the end. Okay, good. So that's what I need at the end. So the idea is going to be that I need to get out something here that lets me use v to bridge to m and p. So how can I use v? Well, v is an id a, n, and p. And so I can use v, and the way I'm going to use it is I'm going to compute a function by induction. And that function is going to, the function that, this is the brace part, is going to have type id a, let's do this right, it should be np arrow id a mp. Because then I can use the v data, apply this function to v, which I've done here, and get my id a mp. So then this tells me what the motive should be. Let's write it as, what did I write it as? The motive should be x, y. I don't need anything. And what I'm actually proving is anything that is, if y is equal to p, then x is equal to p. That's my p written out here. Is my motive. Can you read that? Is that too small? Is that okay? So if you think about it, what I did is I strengthened the induction hypothesis. And this says what I'm going to prove by induction on u is a proof that m is equal to n, that anything equal to p is, if y is equal to p, then x is equal to p. That's what I'm proving. Okay? So then when I plug in m and n here for x and y, I end up with, if n is equal to p, then m must be equal to p, because I'm going to show generically this fact in a second. And therefore, by applying it to v, I will get the desired result. Okay, so I actually didn't mess this up too badly. So now the question is, what do I do here? So I have to work generically here in x, and I have to compute a function. And what does its type have to be? That anything equal to p is itself equal to p, because I have to plug in xx here. So this will be the identity. Let's call it w, lambda w, w. The identity function. And then I'm done. Because this type is id a xx arrow id a xx. Trivially. Okay, that's the type of that guy. So, and that indeed is the xx whatever instance of that motive, which means that this has this type because u has that type m and n. We plug them in here, and then I discharge it, the hypothesis, and get that. So that's a proof. Did I mess it up? God damn it. What did I do?
It's the identity function of id xp, not xx.
Oh, xp. Yes, I'm sorry, not xx. xp to xp, yes. Yep. Okay, I did mess that up. Okay, yeah. It's xp to xp. Yeah, sorry. I mean, I instantiated the motive with x and x, and I mistranscribed it. Sorry. Yeah. Okay, so that gives, that's the proof. And notice, at the very least, and now this is where an issue is going to come up, trans of, oh boy, let's write it down in here. Let's see, which way is it? It's going to be this way. M, P, let's write it, REFL. If I put REFL here and Q here, I think that will work out to be Q, if I'm not mistaken. Should be definitionally equivalent. I hope I just said that right. The reason being, J, this is defined by induction on U. So if that turns out to be reflexivity, by virtue of the fact that these two things are identical, then whatever else I plug in for P and whatever else I plug in here, I will end up with the identity function applied to whatever that Q is, and I will get Q. That's what I will get. So in particular, if this itself were reflexivity, let's write that M, then I get back reflexivity as well. I'll just edit that below the line. Yes. Okay? Did you see that? Okay. So that's important to record because we're going to need that in the next lecture. We're going to need that fact. Okay, but I just want to write that down. Okay, so it's a consequence of the way I wrote the code. Okay, that, yep.
You're looking at this as path induction. Is this basically saying that decomposing REFL does nothing?
Yeah. Yep. So, could I say that again? P composed with REFL does, did I use that fact? No. Maybe I didn't answer your, no. I might have misunderstood your.
What this is proving actually defines.
What does trans prove?
Is this saying that post-composing with REFL does nothing?
This equation says that post-composing with REFL does nothing. Yes. This particular equation says that, yes. Okay, well, you're anticipating me. That stuff's going to go in the next lecture. Okay, but yes, that's what we're doing. So, so catching my thread again. So the thing that I wanted to say is that here's, as a homework exercise, find another proof. Maybe find two other proofs, but at least one other. Find another proof that is, another means not definitionally equivalent. So, in other words, to the one I just gave you. In other words, one that has a different sense. Okay? That is, it conveys the argument differently. Okay? So the one I kind of have in mind is works by a double induction. So I basically, from a certain point of view, you could say, I shortcutted an argument. I happened to notice that I didn't need to analyze V at all. And I gave an argument that worked without analyzing V. But you might, another strategy might have been to first do path induction on U, and then within that do path induction on V. And then, at the heart of it, you will be exploiting the fact that you're working with two instances of REFL, and you're trying to say that their composition, that the transitivity REFL followed by REFL is REFL. That's the essence of what will happen. I don't want to like do it for you. Okay, so, but if you do it by double induction, that'll be a definitionally distinct proof that actually has a stricter definitional equation. We won't be able to show this definitionally. We'll be able to only show the REFL part definitionally. My proof happens to to leave Q invariant, doesn't bother to touch it, and therefore you get a stronger property that says it holds for any Q. But this proof, if you do it, will only guarantee that much. So I was kind of interested to notate that at least that much holds, the one on the bottom line. And then depending on the proof you have of trans, you might get more, okay, definitionally. This is a characteristic feature of working in this kind of a type theory is, you know, by and large, equations that you feel hold true hold propositionally. But some pieces of it hold definitionally, and it's nice to know when they do. Okay? And whether things hold definitionally or not is utterly sensitive to the exact nature of the proof you gave. The exact proof. In other words, trans viewed as just an interface, just as an abstraction, doesn't tell us anything, okay, about how it executes and what sort of definitional behavior it might have. The actual code for trans, depending on which one you do, will have different definitional behavior. And sometimes, you know, to make certain formalizations go through smoothly, people will jigger definitions so that the definitional equations fall out in a more convenient way. So you have to get used to that a little bit. It's a bit, from a programming point of view, that kind of thing is not very robust because you're introducing intermodule dependencies. You're saying that the proof of this theorem depends on the exact proof of the theorem you gave earlier, not the fact that the theorem is true. That's like kind of a crappy thing, to be honest, okay? And the modularity issues about these kind of formalized developments in type theory are, I think, not fully methodologically worked out. People really depend at this stage on, I have a linear sequence in my library, and every damn thing I said before to a first approximation, every last thing I said depends critically, the next thing depends critically on all of it. Okay? That typically happens, which is not like that with a piece of code that you usually write. You usually strive to ensure that that's a library and I don't give a damn how it's implemented, and in fact I don't even have it around when I'm writing my code and compiling my code. I just link it later. That kind of thing is not very well developed in the dependent mechanized reasoning world, and and one manifestation of it is that the definitional equivalences that hold of a proof can affect the well-formedness of a subsequent proof, which basically means one piece of code depends on the exact code of something that went before and not merely on its spec. Okay, so one has to be careful about this, okay? So this is an obstacle for, if I looked at everything I'm doing as, forget all about logic, forget all about mechanized reasoning or whatever, if I just looked at this as functional programming, you would kind of pretty soon start to think, you know, this is pretty lousy, okay? This is not the way I learned to program, okay? So there's something to be done, there's work to be done there. So the leap from non-dependent to dependently type programming is perhaps a little bit more complicated than it might sound at first. It's not like throwing in a new base type or something. It's really a different enterprise. Okay, so enough of that. All right, so I'm going to erase that because I need some space. Okay, so equality, thank God, it turns out to be an equivalence relation. Okay, so that's good. All right. What other properties would so here's the inside game of what I'm going to do, the next two things that I'm going to do. The inside game is everything I am doing depends only on the identity elim rule. That is, as long as the identity elim rule is valid, everything I'm saying is stable under future, like any future things I'm going to do. So that's the critical point, is that I'm treating the identity as an abstract type, in that the only way I handle those values of identity type is through the J mechanism. That's the only operation there is associated with that type. So it's important to say that the importance of that will come up a little bit later. All right, so now what I want to do is talk about some other properties that you would expect of something that, because you might ask yourself, I mean, you know, it's kind of obvious the way I've written it down, but just step back for a minute. You might ask yourself a question, which is, why is the identity type so called? What other properties besides being an equivalence relation do I expect of a relation that deserves to be called equality? Okay? That's what I would ask, okay? So what I want to do is I want to talk about what is called I'll do first simple functionality. So simple functionality is this, is that suppose we have an open term, I'll write it like this, F to remind you that it's B, where A and B are types. In other words, that's why it's called simple functionality, where A, B type. In other words, B doesn't depend on X. We'll worry about that case later. Okay, so we can think of this in diagrammatic notation as I have a map from A to B. Not necessarily an element of the function type, but I just have a map from A to B, all right? I have something that has a free variable of type A in it, and it computes something of type B. And so what I would like to do is I would like to say, have the following very elementary idea. If you give me, so I really need, let me write them down here. Give me X, Y, and A, and U, let's say, which is a proof that X is equal to Y, then I expect this map to behave functionally. That is, it should send equal arguments to equal results. So what does that mean? It means that in B, I should expect Fx and Fy to also be equal. In other words, if you read this logically, if X is equal to Y, then Fx is equal to Fy, and this would happen in B. Okay? That's what we're saying. So the question is, there ought to be something that goes there. Okay, and that's the point. Okay, so that's what I want to do. So that just says the maps preserve equality. So this is really saying something about id, you see, because, of course, if I just wrote down some j random r here, which was some binary relation that I cooked up in my head out of nowhere, it wouldn't necessarily, you wouldn't think that all maps must respect r. You wouldn't, like for any r that you randomly put down. But id is a special one, okay? It ought to have this property. So the thing is, how do we do this? So I want to define, so the goal is a functional programming problem, is I want to define app f to u, that's what it's called, okay, and that could be read as apply to path, or it's sort of the functorial action. So there are other notations that people have used. I won't use them, but sometimes people use banana brackets for this. Okay, so f applied to u. So another way of thinking about what I'm doing here, which is foreshadowing what I'm going to say very soon, is I'm looking at f knows how to act on the endpoints of this path, if we think of that as a path. I want to lift its action to the path itself. So I want to talk about what f is u. So this could also be called the functorial action. And that's really an abuse of terminology right now because I haven't established that I have a category involved, let alone a functor. So, but we'll get back to that later, okay? So right now that's an abusive terminology, but it'll turn out to be accurate. So I want to define appfu, which has this type, okay, with the above type. Okay, so what is appfu going to be? Well, sort of the only thing I can do is define appfu by some sort of path induction on u. It's the only thing I've got, the only game in town. It's the only thing that I have around here. And so what is the type of u? The u is id_axy. I want this whole thing to be a path that is a proof of id_a. So this one is really easy, fy. So I have to figure out a motive that would take me from when I finish doing this that would get me to this instance. And the motive that I could use, what notation is x, y, I don't care about this, id be fx, fy. Or for shorthand, I could write this as id be f blank, f, double blank, okay, something like that, to say that's my motive for the induction. And then what I'm going to do is I'm going to plug in the endpoints of u, which are x and y, into that blank, and I get what I want, provided that generically in x, I can give you something, and what does its type have to be? It has to be id be. If that's the motive, then its type has to be id be fx, fx. And so it's going to be reflexivity again, our old friend reflexivity at fx, if I didn't make a mistake. I screwed it up again, did I? What did I do? Reflexivity at B. Okay, yeah. All right, yeah. What else did I do? It'd be, yeah, that should be a B. Yeah, okay. These are very minor mistakes. Okay, I will give myself partial credit. Okay, so, all right, so this is the, that's the J. That's what it is. That's what the application is. Okay? So this tells us now that all maps are going to respect the maps from A to B are going to respect, I'm having a bad eraser day, okay, are going to respect equality. And now there's another interesting one that comes up, which has to do with families of types. And for those of you who are au fait with such things, remember I have not yet introduced universes, so in the logic of my development, this is a separate, like completely separate thing. So the other thing I want to mention is this. Suppose we have, so this is what is called the transportation property, or the respect of families, so I'll call this transportation. So if that was called functionality, this is called transport or transportation. And this is a very important thing, which is, suppose we have a family of types. So what did I call it here? So I called it B is a type, and for some reason in my notes I called it Z, so I better not cross myself. Let's do it like this, okay? So I'll write it like that. No, actually I was totally inconsistent. Let's do it like X, and I'll think it out. So we have a family of types, okay? So the idea here now is how do we think about a family of types? So this is the useful thing. So two pictures are kind of useful, okay, that we're going to write down, and this is what I'm going to show next. So picture number one is what we think of is we think of assigning to A and A, we send that to a type, which is B of A. All right, write it like that. And for each possible A, so if you had another A prime, then you would send that to some other type, B of A prime. And for all I know, they're the same type, so don't draw too many conclusions from the picture. It's a little deceiving sometimes, okay? But the idea is that each of the elements of A, you can think of a family of types as some kind of mapping that sends each element of A to, well, I'm writing it as kind of a balloon, to something which is itself a type. So there's all these little B of A's in here, and there's all these little B of A primes in here. And for all I know, those are exactly the same balloon, but I'm not saying that they are or they aren't. So I have this picture here, which is A, and this is my B of A and B of A prime. So that's one way to imagine what a family of types looks like. For a lot of times, that's kind of the natural way to do it. Another way to imagine it is instead this, is what you think of first is a big disjoint union of all of those guys, which I'll just call B. And you think, so I'll draw it like this. This will be my big disjoint union. So this box thing comes down to here. And you think of it with a picture like this. This is A, and this is, well, the total space. So this is sometimes written like that with a big S or integral sign like that. And the idea is that what you think of is down here are my A's, like A and A prime. And I have what is called here a display map, which tells you for each element of this big disjoint union, where did it come from? So the way to do this is, the way to depict it is you say, what you do is you just reorganize everything so that all the stuff that lives over B of A is thought of as inhabiting that line. So this is B of A. So what I do is I smush this stuff, I reorganize all these guys here, and I stack them up like this. And I make that line. And that line is designed to sit right above A. So this line is sent to little a down here. And then this line, so I reorganize these guys and line them all up, get everything organized like elementary school. Everybody stand in line. And we put them in line like that. And everybody lines up. And then we say, okay, all you guys are, homeroom 2. Okay, and so we write it down. We tell you what your homeroom is. So this is everybody in that homeroom, and this is everybody in that homeroom. And we line them all up. Okay, that's what we're doing. And that's called the display map. The display map is telling you, for every single student, will tell you what their homeroom is. Okay, so that's what's happening here. And then that way, we've quite literally sliced up the total space into all the pieces. And these individual things are called the fibers. Okay, that's the terminology. Okay, so that's the way you think about it. Okay, so this is these are two pictures. I'm going to make these technically precise. Both of these pictures will be made technically precise once I introduce the idea of a universe. I'm going to need this, and here I'm going to need a sigma type and stuff, but I'll need also this transport property, so we'll get to that. We'll use sigma types to make that technically precise in a moment. But these are like images that it's useful to have in your mind and thinking about it. Okay, so that's two ways of thinking about families of types. So I have such a family of type. And now what I want to do is I want to claim that if these two guys are equal, that is, I have some path between them, or an identification between A and A prime, then I want to claim that that gives me a way of moving or transporting, that's what this is called, students from homeroom 1 into homeroom 2 because these are equivalent. Okay, these are equivalent homerooms. So the idea is that this guy over here, every single one of them, but this guy over here will get sent to this guy over here. That would be the idea. In other words, there exists a guy over here which is being sent by this identification, this path P, will be sent from here, and that will be called, the map is called P lower star. Okay? And that is called a lifting property. Okay? So this is called what is called the lifting property. Because I'm lifting the path in the base space. So this is, by the way, this is called the base space. This is called the total space because I'm summing it all up. Okay? The display map will have the characteristics of a fibration, which I'm going to explain in a minute. And the characteristic of being a fibration is that if you have this kind of identification here between A and A prime, then that will induce an identification between the two fibers. In other words, it's a lot like saying, if you look at this on the functional side, it's a lot like saying, if A is equal to A prime, then in some sense, B of A is equal, I'll write a funny notion of equal here, to A prime. This is ultimately what we're going to prove. This is what we're heading toward. Because if these two homerooms are actually the same one, they just have different names, then the students that are in one are exactly the same as the students in the other. If we think of it as a set, then it's a one-to-one correspondence. So for sets, this would be bijection. This would mean bijection. Okay, that's what I'm heading toward. That those two things should be exactly the same. Well, why? Because what we're going to see is that, remember that the identity type is symmetric. So if there's an identification from A to A prime, there's a symmetric one from A prime to A. So I can send these guys back, and then we can study the algebraic structure of that sending back and forth, and it will work out that it's going to be a bijection in the case that those are sets. So I'm foreshadowing a lot of things, but I want to give you a feeling for where I'm going in order to motivate what I'm doing next. So transportation could also be thought of as functionality for families. And that terminology of functionality for families is more motivated by this picture. If we think of ourselves as having a function from A into the universe of all possible types, then I want equal arguments, as I did over there with simple functionality. Equal arguments here should give me, well, that's the issue, equal types, whatever that means, okay? And that's the problem. That's the whole issue. That's the entire issue. What does it mean to be equal types? Okay? So this part is now vague, right? I haven't defined that notion yet. I was giving you a hint about it. Okay? So we're gonna have to make that precise, and we will. Okay? But that's what we're doing. So the ground zero for this, the way we get started is with transportation, is I want to say there is a map. So if we have this, okay? So given with the following property. So if I have U, let's call this, so let me just get my notation down here. Okay, so I have M and M prime in A. I have U, which is an identification of M and M prime. Okay, I have that. Okay, and I have V, which is in M for XB. Then there's a map called transport, which is written like this, for the family x dot b that I'm dealing about here. So that's kind of the motive, U and B, which gives me something in M prime for x b. Okay, so I claim there exists such a thing, and I have to define that. Okay, that's what I want to do. Equivalently, I could just say, given M prime and U, I have a function from M of xb to M prime of xb, and then I would drop off the applied to V part. So that doesn't make any difference. Okay, that's the same. And this is often notated as U lower star of V. Okay? That's the notation. So the problem with this notation is you're supposed to know what x dot b is, because the action depends. I mean, it's the action for a particular family. So this notation is a little a little too shorthandy. The full notation is that, but a lot of times people write U lower star v. So that's what I did here. Let me make my letters line up a little better. So call these M and call this M prime. This is my U. Okay, so that the letters look the same. And then we say we have U lower star takes V in the fiber over M and turns it into something, transport of V along U into the fiber over M prime. Okay, so that's the picture. So this picture is written here, and I started to mention before, that's called the lifting property because the path U is lifted to the total space up here to a path U star between the fibers. Okay, so that's what the way, if you think of this as sitting above that, then this is being lifted up to that. That's the way the terminology goes. Okay, so how do we define this guy? Well, we're going to define it by a transport. So it's defined to be, a path induction. So what I do is I'm going to take a J, and actually I'm just going to apply this to V. So the whole thing is gratuitously eta expanded. I could have just written it as a function, but that's okay. I did this, all right? And what do? Is we use the following motive. We have, the motive is xy underscore, and in fact what I do is I write that function, and it takes, that's why I called it z before. All right, now I know. I like z after all because it will help me do something here. So we do x for z and b, arrow y for z and b. So it turns out I'm gonna compute a function and then I'm gonna apply it, okay? And I'm gonna work on u, so I'm gonna examine u. So u is my path from m to m prime in A, right? So this is a proof that m is equal to m prime in A, okay? And I'm going to do a j on that guy. So whatever I do, I haven't finished filling it in, but whatever I do, its type will be, plug it in, m for zb, arrow, n prime for zb. So if I apply it to v, which is my m for z, then I'll get something in the right fiber. So I'll at least have that much going. So the sufficiency for that is to show something that works for xx. So, or just call it z, b arrow b. So I'll write z dot the identity function, lambda ww, whose type is b arrow b. Remembering that b has a z free in it, okay? So that's what we've written down there. And then we're done. Okay, so that's the idea of transport. Okay, good. And now I want to, we're over time. I wanted to do one more example. I started a little bit late. Are people like banging at the door? No. I wonder why. Do you mind if I I'll do one more example? Okay. An example of this, which is the following thing. Okay, so the example is, find a map with the following type. If we have x, y, and nat, and assuming we have this vec we've had before, v is in vec of x, or sec of x I called it, something like that, sec of x, let's do it like this, x, y, and nat. I want to map something which goes from sec x plus y to sec y plus x. Remember we talked about the fact that although for every single instance, if I plug in numerals for x and y, these are definitionally the same type. When I reason generically, they're different. Definitionally, they're distinct. So we can compensate for that by saying that anything I have in here, I can transport over here, and symmetrically, anything over here, I can transport over here. Okay? So it's going to break into two parts. Okay? You need to find a path between x plus y and y plus x, and then you transport along that path. And as a programming exercise, this is a little tricky if you've never done it before. And I use two lemmas are useful to isolate here. You'll find out, okay, to help you. I want you once to actually write out the code. Right, there's a recursor in here. okay? And I want you to do that once. I want you to do that once because you should understand the detail of how it works, okay? And then use transport. All right, so we'll pick up next time. I'm running over time, sorry.